Welcome to Real Learning Center, where we focus on real learning. So today we are going to basically take you into the third video of heat, series heat of 6 videos. In the last 2 videos, we actually learned fundamental concepts of heat, where we talk about temperature, heat, internal energy, specific heat capacity, and thermal expansion. These are the things we learned in the first 2 videos. In this video, we are going to learn about how heat gets transferred from one place to the other. In fact, the whole heat transfer is split into 2 videos. Okay, so let's start with the first video now. So we are going to now look at the heat 3 video, where we will understand how heat transfers from one place to the other place. Okay, so now if you look at basically a heat transfer, we know that heat transfers from hot object to the cold object. The hot object it flows into the cold object. And we also remember that we talked about in the first video, a fluid caloric goes from hot object to the cold object. And that theory, though believed for more than 100 years, was later discarded. Okay, now we have new theories on how actually heat is transferred. So now the question basically is, how is the heat transferred from hot object to the cold object? So heat doesn't transfer in just one way. It transfers in 3 different ways. So what are those 3 modes of heat transfer? We are going to see that now. Okay. The first one is the simplest one. So there is some fire, and you're going to take a metallic stick and try to hold it on the top of the fire and touch the fire. So you can very clearly see that within a few minutes your hands will get burned and feel hot. So that's because it's a metal and it conducts heat. So that is called conduction of heat. So heat actually travels in the metal to your hand, from the fire to your hand. So that is mostly it happens in solids. So this kind of conduction kind of heat transfer mostly happen in solids. Okay, now let us see what happens if you actually take your hand, and instead of holding it there, I keep my hand on the top of the fire. Okay, so if you keep your hand on the top of the fire, if you don't take it very nearby, if you take it very nearby, quickly get burned. If you take it a little higher, slowly, but it will heat up your hand quite fast, in fact. Okay, so what really happens? So what happens is the air which is on top of the fire gets heated up, and that air goes up. So when it goes, because when air molecules get heated up, so they get lighter, and they keep going up, and it hits your hand, and it gets transferred to your hand, the heat. So you feel hot. Okay, so this kind of a transfer of heat is called as convection. And this convection actually happens mostly in liquids and gases. It doesn't happen in solids, because solids, the molecules cannot move. They just stand there and jiggle. They don't move. In liquids they move, and in gases also they move. So that's why convection happens only in liquids and gases. So instead of actually keeping your hand on the top of it, let us say you keep your hand by the side of it and sit there. So would you get hot? Now, would it burn your hand? Now we all probably one or the other day have done this, put some fire in the middle and sit around the fire and have your night camp or something like that, with the fire in the middle and people singing around. So everybody actually feels nice warmth, but nobody gets actually burnt. Okay, so how does the heat transfer now? See, you know very well that by the side of the fire, the fire is here, by the side of the fire, the air gets hot actually, because it is touching the fire. But that air goes up and doesn't come to your hand. So your hand does not get burnt. Since it goes up, it doesn't go by the side. Because it is lighter, it goes up. So how does it come to your hand then? What comes to your hand? So the heat somehow comes also to your hand, and that actually is a new mode of heat transfer called as radiation. For radiation, there is no medium required. So it doesn't actually transfer through either solid or liquid or gas. It just transfers in, it can even transfer in vacuum. Suppose if you sit around it, if there is a vacuum too, okay, then even then you will feel hot. Now how do we know this? Have you ever done any experiment with vacuum around a fire? No, but we have a very great experiment that is happening daily. So you look at the sun. From sun to here you get heat. Don't we get heat from sun to here? We get. How does it come? Is there air in between? Maybe there is air in the on the earth's surface, but from sun to here there is full vacuum and the heat is transferred. So that is a mode of transfer called as radiation. So it's very interesting to understand how that heat gets transferred through radiation. We will come to that. Okay. So now we'll just go through these three things: conduction, convection, and radiation one by one a little bit, and understand a little more deeply. So conduction is quite apparent in the this particular animation. You can watch here. So there is this metal bar, and inside the metal bar I have just expanded it. You can see that these molecules are actually jiggling. Now they are very small, the metal atoms. They are jiggling, and the moment you put some fire by the side of it, so the heat energy gets transferred to those molecules or the atoms, as the case may be, and they start jiggling more. So when they start jiggling more, its neighboring atom also jiggles more, and its neighboring atom also jiggles more. So the jiggling continues till the other side, and that we call conduction. So if you happen to touch on the other side of the metal, the jiggling that is happening on the solid will get transferred onto your hand, and the molecules in your hand start jiggling. So when that happens, you feel heat. That's when you feel heat. Okay? When the molecules jiggle on your skin surface. So this is one mode of heat transfer. It's just everybody is jiggling more and more, and that continues to the other side. So this is called conduction. This happens mostly in solids and a little bit in liquids also, but liquids molecules themselves move. So conduction, though the conduction is in most of the liquids happen, but now we have seen that some solids actually are much more conductive than the others. Now you take a glass rod and a metal rod in one hand, in the other hand metal rod, and put that both into the fire. Which one will get burned first? When there is no prize for answering, metal rod gets burned first. So, but glass rod also will become warm. So glass conducts heat, and metal conducts the heat faster and better. Okay. So what is the difference? Why does metal conduct better than glass? So if you watch these two animations, you will actually know why that is so. Okay, let's just watch these two animations. One of them is the glass rod, the other one is the metal rod. Just watch it. So your fire on the other side, hand on this side, and it is jiggling. So both of them are jiggling, you can see. But you can very clearly see in the case of a metal rod, there is a few more. The blue ones are also marching towards this side much faster. So what are those blue ones? So the blue ones are actually electrons. I mean, electrons are not blue. I will just put them as blue. Blue ones actually march through that. So metal actually has a lot of free electrons. So once the atom starts jiggling, it will actually make the electrons also gain some kinetic energy. Okay. Electrons will start moving very fast. When they move very fast, they come to the other side, and it will hit other atoms. And those atoms will take kinetic energy from the electrons and start jiggling. So the glass rod actually has to continuously depend only on atoms jiggling to the neighboring to its neighboring. But here there is one more thing which moves faster than that is electrons. And those electrons also carry kinetic energy. And because of that, though solids are good conductors, metals are amazing conductors. They conduct much more because of those free electrons which move very fast inside the metal. Okay. So now you know why conduction is better in metals, because it is aided by those movement of electrons. Okay. So now let's look at the next one, which is convection. How does convection happen? So we know how conduction happens, quite simple, jiggling and electrons. So how does convection happen? Let us take a case of a geyser, water heater basically. So you can see that at the bottom of the geyser there is one one heater filament will be there. Okay, a coil, electrical coil. So that heats up. So when the electrical coil heats up, the neighboring molecules of water get heated up. Okay. Once they get heated up, they get lighter. Okay. Once they get lighter, they start going up. So the hot water actually goes up, and to occupy that place, the cold water has to come down. So the cold water comes down after that. So when cold water comes down, you can see that it kind of forms a circulation. So hot water going up, cold water coming down, hot water going up, cold water coming down, like that. So this kind of a circulation is called as convection current. If convection current cannot be set up, okay, then all the water inside that will not be heated up. Assume that if that doesn't happen, okay, the water around the geyser, around the coil will get heated up and remains hot. All the remaining area of water will be cold. Will that happen? No, no. We know very well that when the geyser heats up the whole water. So here is a small thought-provoking question. Okay. So instead of fixing that coil at the bottom of the drum, let's say I fix the coil at the top of the drum. So will our water heater or the geyser still work? Will the convection current set up? Think about it. Okay. Now let's see whether the convection current, how does it get set up in gas. Okay. So sun actually heats up the surface of the earth much faster. Okay. It has low specific heat capacity. It gets heated up very fast. So once the surface of the earth gets heated up, then what happens is the air that is touching the surface of the earth, that gets heated up. Okay. And once that becomes warm, it actually rises up. So once the warm air rises, then what happens? To occupy the space, the cold air comes down. Okay. So now that process continues. When that process continues, you see that circulation. Warm air rising, cold air coming down. Warm air rising, cold air coming down. That is basically the circulation of wind. So that's how all the atmosphere gets warm. Okay. So and wind also blows because of that. Now this is basically how convection happens in the gases. Okay. Even in gases, convection can happen, and we saw how it happens in liquid. Now we have kind of got an understanding of this convection. Now conduction we know, convection we know. So before going to radiation, we have one more question that we need to ask and get an understanding on. Okay. So that is basically, let's say you keep a hot cup of milk. It is at 80 degrees centigrade. So if you keep it like that, slowly it cools down. Okay, we know that. And let's say I keep it inside a big water pond of about 20 degrees centigrade. So this is not a pond, this is just a beaker, big beaker. I can't put a pond there. The reason I am talking about pond is I don't want the temperature of that to rise. Okay? So it's sufficiently big. Now this is 80 degrees, this is 20 degrees. So difference is 60 degrees. So what will happen now? So gradually the temperature of the milk comes down and becomes cooler. Okay. So now the question that has that you have to think about as a physics guy is to calculate how fast. Now how fast will it cool down? So will it cool down very slowly or very fast? Now what is the rate of cooling? So let us say, okay, the milk slowly cools down, and after 20 minutes it will become 50 degrees. I mean, I have given a little more time, but actually it can happen faster. Assume that after 20 minutes it will become 50 degrees. Now my question is, this is your data. So my question is, after how much time, okay, will it become 35 degrees? Why am I asking 35 degrees? Because, so you look at this, from 80 to 50, okay, it is about 30 degrees down. Okay. Now 15 to 35 is about 15 degrees down. Any intelligent boy will quickly look at it and use his ratio and proportion knowledge. 80 to 50, it came down in 20 minutes. That means 30 degrees it came down in 20 minutes. So to come down for 15 degrees, half of it, which is 10 minutes. In another 10 minutes, it will come down to 35 degrees. But apparently, that is a wrong answer. So because Newton, actually, you know, heard about Newton. Newton actually, great scientist. Now he always used to think about many things. So one of them occupied his head, and he came out with a lot of observations, and he came up with his own law called as Newton's law of cooling. So what does that say? So he realized that 10 is the wrong answer for that after doing many experiments. So then he came out with this law. So he said, according to Newton's law of cooling, basically he says that the rate of cooling is directly proportional to the difference in temperature between the hot body and cold body at any given point in time. A long statement, okay? But it has very simple meaning. The meaning is very simple. So let us say there is one hot body and there is a cold body. If the temperature difference between them is very hot when compared to this, okay, then it cools down quickly. The rate of cooling is higher. That means rate of cooling is more when the difference is more. The other one is when the rate of cooling is less. That means only small difference between these two. In that case, it also cools down slowly. Okay. That is all this statement is saying. Rate of cooling is proportional to difference in temperature. Now let's apply this to our question, okay, our milk cooling down question, and see what happens. See, the tricky part is this: milk starts cooling down. As it cools down, at every instant it comes down a little bit. Its difference in temperature with respect to the pond is also less. So now from here to here, whatever speed it cooled down, from here to here it cools down with lesser speed. From here to here, lesser speed. Here to here, even lesser speed. Like that, as it decreases the temperature, the speed of cooling also decreases. That is his law of cooling. He came up with a lot of mathematical formulae for that, which I am not going to write here on the board. Okay, so we will just calculate with common sense using this particular statement of Newton. So the hot cup of milk at 80 degrees and pond was 20. What was the difference? Difference was 60. Okay. To be able to basically come down to 50, from 80 to 50 it came down, which means 30 degrees. Okay. It took 20 minutes to come down by 30 degrees when the difference was 60. Now what happens? Next scenario. Now next scenario is the difference is, it is already 50, the pond is still 20, 50 to 20 difference is 30. Earlier difference was 60, now the difference is 30. That means rate of cooling also has to be lowered. It cools down slowly. How slowly? Half slowly. Okay, almost like that. Now, to be able to go down from here to 15, it would take the same amount of time when it was going down from here to 30 down. Here to 15 down takes same amount of time as here to 30 down, because rate of cooling is halved. That means in next 20 minutes, it only reduces by 15. So the answer to that question is, it will become 45. Okay. It will become basically not 45. How much was that? 35. It will become 35. Okay. In next 20 minutes. Okay. It loses 15 degrees in 20 minutes. After that, the difference is just 15 now. Okay. Then it loses 7.5 degrees in 20 minutes. Okay. After that, it would lose 3 3/4 degrees in 20 minutes. For every time to reduce it to half, it takes the same amount of time. To reduce it to half of this takes the same amount of time. So we call this half-life. Okay. So we understand it when we go a little further and study a deeper deeper class, no, higher classes when we actually mathematically model them. At least this much now you understand. Okay. So now we'll move forward. So this is Newton's law of cooling. So now we'll move forward and see what is this new one called as radiation. Okay. So now what I am showing you here are some pictures. So these are not drawing, and these are not devils, these are human beings. Okay. So these pictures are taken natural pictures, but they are taken from a special camera called as infrared camera or a night vision camera. It's just a cup of coffee or something like that kept, and that other one was basically a boy standing with an ice spear in his hand, and the three people sitting and chatting, and this is Earth. Okay. So all this are actually, from where are they giving? Where are they giving light? How is light coming out? Is the boy giving out light? So that is a question. Okay. So the answer to that question is actually yes. Everything and everybody above 0 Kelvin, okay, radiate energy in the form of electromagnetic waves. Whenever we say electromagnetic waves, the meaning of that is light. Okay. Electromagnetic waves, and we just need to have a right kind of eye to see it. Okay, we can't see it in our naked eye. We have to see it through night vision goggles or night vision cameras to be able to see it. Okay. So what is this radiation? How can we see it? How to actually, why does it emit, why do we emit radiation? Okay, these questions basically we need to answer. Okay. So that is when we actually understand, see that dog, it is really radiating. So how does it radiate? What is happening inside? So that part we are going to study is actually in the next video, where we go a little deep down into radiation. So now before we end this video, let's take stock on where we stand. We completed actually temperature, we completed the heat, internal energy, we understood specific heat and capacity, thermal expansion, and we now understood heat transfer to some extent. We understood conduction and convection. Radiation, we saw what it was, and we still have to go a little deeper into it. And Newton's law of cooling, we understood how things cool down. Now we still need to actually finish radiation to the full detail, and then we're going to the change in state or phase change. So now before moving forward, I'll finish like every other video with some questions. Okay. So the questions are, the first question is, suppose, actually you can hold your finger besides the candle flame without harm, but not above the flame. You take the candle and hold your hand by the side of it. Nothing happens. You can even touch the flame like this. Nothing actually happens. Try it out in front of the parents. Okay, don't do it on your own. So try it out. And if you keep your hand on the top, it burns, but by the side it doesn't. So why so? Think about it. Okay. And second question is, when a hot object warms a cold one, okay, the increasing temperature of the hot object, of the cold object, and decreasing temperature of the hot object, are they equal? That is the question. Okay, is it equal? What I am asking basically is, there is a 100-degree object, another 50-degree object. Okay, if you basically put them together, okay, now 100 will become 75, 50 will become 75. So that means this decreased by 25, this increased by 25. Okay, is this true? Does it average like that? Think about it and answer. It's not it's a tricky one. Okay, think and answer. Does it average like that? Does it become equal? Decrease here and increase here. Think about it. And then the last question is, you have observed probably, room heaters are generally fixed at the ground level, and the air coolers or air conditioners are fixed at the top level. Why is it so? Has it got anything to do with convection current? Think about it. It is very important. If you fix the AC somewhere down and heater on the top, will it work? Think about it. Okay. Thank you, and let's continue this in the next video. Bye.